Hello everyone, welcome to the NN Classroom. Today I'd like to share with you a past paper question from 2019, time zone 1 in May, so question number 18, relating to topic 6, kinetics. Let's see, which properties can be monitored to determine the rate of the reaction, so that means now we are looking for some parameters that can be changed, and so we can monitor, and so reflecting the progress of reaction, and so we can find the rate of that reaction, right? Students should have realized that in topic 6, we learned so many methods, but what is said to be a suitable, appropriate method is that something that is measurable, and the so-called measurable is something that we can observe or we can detect, and that change is possibly changing during the progress of reaction, right? So in this case, let's see the several choices. The first is the change in volume. Supposingly, anything that is measurable in terms of changing volume must have gas involved. LVD, right? Because gas is the easiest one that can be measured using like gas syringe, pressure sensor, or any other parameters that take a look into the gas volume. But unluckily, in this equation, is there any gas involved? No. So that means the change in the volume should be negligible for this chemical reaction, as the solution containing some solid finally get to a solution containing some solid, which means the volume change is negligibly small. It's kind of quite impossible to be measured because no gas is involved. It's either produced or consumed? No. So that's why change in volume is quite impossible. First of all, a really common technique is that if student can recognize that one is never be possible, then actually we no need to look even further because the answer can only be C, right? But for the conceptual wise understanding, we should look for why 2 and 3 are possible. For 2, let's see, change in temperature. This time is possible because this is going to be what we call a displacement reaction. A really classic type of reaction that involving a more reactive metals reacting with a less reactive metal ion, so copper 2+ in this case, and then they swap the position, right, in which the iron now sacrificed to form the iron 2+, and the copper 2+ is now reduced back to the copper metal. And this is going to be a redox process. And all those kind of spontaneous, automatically running displacement redox reaction are all going to be exothermic. And this is all going to be exothermic reaction, right? As we have learned it in topic 5 as well, some examples of reactions that are typically exothermic. So the typical feature of an exothermic reaction is that the temperature is increased. So that's why by measuring the fluctuation of temperatures from time to time, we can monitor the progress of reaction. So that's why statement 2 possible. Finally, the color change is also possible, as we can realize that this particular reaction is actually having a change in color. As we see, first start off with copper 2+, and we notice that copper 2+ is a blue ion, right? Yeah, this pretty famous transition metal ion is going to be bluish in color. And after the reaction, it turns out becomes iron 2. Iron 2 is actually having a greenish color. Green color, right? Yeah, if it is under high concentration. Under relatively low concentration, it still appears to be pale green. So that's why we should see a pretty obvious color change from the pretty blue solution to a green solution. So that means by measuring the absorbance at a particular wavelength, maybe measuring the wavelength of blue color or green color, then we can monitor the progress of reaction in showing the concentration of that corresponding ions changing. And so we can find the rate of reaction. So that's why method 2 and method 3 are both possible. So that's why the answer for question number 18 goes to C.